Previously, we covered the core foundations. Now in part 5, we tackle Mars. Habitability. Mars once had rivers, it once had lakes. The question we're asking today is whether it ever had life, and whether some corner of it might still. Last time, we looked at the surface of Mars in detail, its canyons, volcanoes, and ancient terrain. Today we're asking the deeper question: could Mars have ever supported life? And what does the science actually tell us? That question matters right now because we currently have rovers, landers, and orbiters actively working on Mars, and the answers they're sending back are changing what we thought we knew. Let's start with what Mars is, before we get to what it might have been. Mars is the fourth planet from the Sun. On average, it sits about 228 million kilometers from the Sun, roughly 1.5 times Earth's orbital distance. A Martian year is 687 Earth days. Its axial tilt is about 25 degrees, close to Earth's 23.5, which means Mars does experience seasons. That detail will matter later. The planet is about half the diameter of Earth. Its mass is roughly 1/10 of ours, and its surface gravity is about 38% of what you'd feel standing here. So if you weigh 80 kilograms on Earth, you'd weigh around 30 on Mars. That lower gravity has had enormous consequences for the planet's history. Consequences that go right to the heart of habitability. Mars has 2 small moons, Phobos and Deimos, but we'll come back to those in the next episode. The surface of Mars is iron oxide rich. That's the rust that gives it its red color. Beneath that surface layer, the geology is basaltic, similar in composition to volcanic rock on Earth. The planet has some of the most dramatic geological features in the solar system. Olympus Mons, the largest volcano we know of anywhere, standing about 22 kilometers above the surrounding plain. Valles Marineris, a canyon system, stretching roughly 4,000 kilometers across, long enough to span the width of the United States. But here's the thing about Mars that matters most when we're talking about habitability. Mars was not always the cold, dry, thin-aired world it is today. The evidence for a warmer, wetter Mars is written into the geology itself. And this is where the story gets genuinely interesting. Around 4 billion years ago, during what's called the Noachian period, Mars appears to have had a much thicker atmosphere, substantially higher temperatures, and liquid water flowing across its surface. We can see the fingerprints of that era everywhere. Ancient riverbeds, dried up lake basins, deltas, where rivers once emptied into standing bodies of water. Minerals that only form in the presence of liquid water, including clays and sulfates, detected from orbit and confirmed on the ground. Gale Crater, where the Curiosity rover has been working since August 6, 2012, was almost certainly once a lake. Curiosity found mudstone sediments, the kind of fine-grained rock that settles out of calm water over long periods of time. It found the chemistry. It found the mineralogy. The case that liquid water once sat in that crater for potentially millions of years is solid. Now here's the open question that we need to hold on to as we go through this. If Mars had all of that, water, chemistry, geological energy, why did it lose it? And what does the answer mean for life? The short answer is that Mars lost its global magnetic field. But the full answer is more complicated. Mars today has no planet-wide magnetic field. Earth's magnetic field is generated by convection in our liquid iron outer core. Essentially, our planet's interior is still churning, still generating a dynamo. Mars, being smaller, cooled faster. The evidence suggests its core solidified and the dynamo shut down somewhere between 4 and 4.2 billion years ago. Without that magnetic field, Mars lost its protective shield against the solar wind, the stream of charged particles constantly flowing out from the Sun. Over hundreds of millions of years, the solar wind stripped away the Martian atmosphere. As the atmosphere thinned, atmospheric pressure dropped. As pressure dropped, liquid water became unstable at the surface. It would either freeze or evaporate. The planet's greenhouse warming collapsed, and Mars became what we see today, a world with an average surface temperature of around -60 degrees Celsius, dipping to -125 at the poles in winter, and climbing briefly to around 20 degrees near the equator on a summer afternoon. But that warmth doesn't last, and the pressure is so low, less than 1% of Earth's atmospheric pressure at sea level, that liquid water cannot persist at the surface. That's the transition, warm and wet, to cold and dry over geological time. And it's that transition that frames everything we want to understand about Martian habitability. So what actually counts as habitable? When astrobiologists talk about habitability, they're not asking whether a place is comfortable for humans. They're asking whether it meets the basic requirements for microbial life as we understand it. The bare minimum, liquid water, a source of energy, and the right chemical building blocks, carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. Mars has ticked most of those boxes at some point. The water was there. The chemistry was there. Geothermal energy from volcanic activity almost certainly provided heat. Hydrothermal systems, places where hot water meets rock, are considered some of the most promising environments for life to get started, and Mars almost certainly had them during its Noachian period. Here's something worth sitting with. On Earth, the earliest evidence of life dates to around 3.5 to 3.7 billion years ago, possibly earlier. The window when Mars was at its most habitable overlaps with that same period. Both planets were warm and wet at roughly the same time. Life got going on Earth. The question of whether it got going on Mars, even in microbial form, is not a question we can yet answer. But it's not a ridiculous one. The Perseverance rover, which landed in Jezero crater on February 18th, 2021, is specifically designed to address this. Jezero is an ancient lake delta, one of the most compelling sites on the planet for preserved biosignatures. Perseverance has been collecting rock cores from the delta, sealing them in small metal tubes, and leaving them on the surface for a future sample return mission to bring back to Earth. Those samples are the best shot we currently have at detecting whether Mars ever hosted life. Perseverance has already found organic compounds, carbon-based molecules in the Jezero rocks. That's not evidence of life. Organic molecules can form through purely non-biological chemistry, but it confirms the raw ingredients were present. What we need is patterns in those molecules or structural features in the rock that can only be explained by biology. That analysis will require laboratories on Earth. Now, here's the question we opened earlier. If the surface of Mars became inhospitable, does that mean life, if it existed, simply died out? Or could it have retreated somewhere? This is where the science moves carefully, and honestly, it has to. But there are serious researchers asking this question, and the answer isn't simply no. There are places on Mars that are significantly more sheltered than the open surface. The most discussed candidate is the subsurface. Several kilometers below the Martian surface, geothermal heat might still be enough to maintain pockets of liquid water, possibly briny water, since dissolved salts lower the freezing point significantly. In 2018, a team using the Mars's radar instrument on the Mars Express orbiter reported a radar reflection beneath the South Polar ice cap, consistent with a subglacial liquid layer about 20 kilometers across. That finding has been debated. Follow-up studies have produced competing interpretations, and the scientific community has not reached consensus. But the possibility of subsurface liquid water on Mars today has not been ruled out. Then there are the poles themselves. The Martian polar ice caps contain water ice, not just carbon dioxide ice, though both are present. The residual North Polar cap is predominantly water ice. That's a significant reservoir. There's also been interest in deep subsurface environments where radiolysis, the splitting of water molecules by natural radioactivity in surrounding rock, could provide chemical energy for microbial communities without any sunlight whatsoever. Environments like this exist on Earth, deep underground, and host microbial communities that have been isolated from the surface for millions of years. None of this is evidence that life exists on Mars today. Let's be absolutely clear about that, but it demonstrates that the surface conditions are not the whole story, and that the search for past or present life has to account for environments we can't yet directly sample. What we can say with confidence is this: Mars had the conditions for life. It had them for a long time. What happened to those conditions is reasonably well understood. What happened to life, if it was ever there, is the open question of a generation. There are a few other facts about Mars that are worth placing in this context. Mars orbits the Sun at a distance that varies significantly across the year, more so than Earth, because Mars has a more elliptical orbit. At its closest approach to the Sun, Mars receives noticeably more solar energy than at its furthest point. Combined with its axial tilt, this produces dramatic seasonal changes, including massive dust storms. In 2018, a global dust storm lasted for several months and was responsible for the loss of the Opportunity rover, which ran out of solar power when the sky was blotted out. Dust on Mars is a genuine environmental factor that any life or any mission has to contend with. The Martian atmosphere is about 95% carbon dioxide, with small amounts of nitrogen, argon, and trace gases. The methane question has been one of the more controversial threads in Mars science. Curiosity has detected what appear to be seasonal fluctuations in methane levels in Gale crater. Methane on Mars is puzzling because it should be destroyed by ultraviolet radiation relatively quickly. If it's being produced, something is replenishing it, either geology or, speculatively, biology. European instruments in orbit have not consistently confirmed the same detections, so the methane situation remains unresolved. It's an example of Mars science being genuinely messy and ongoing, which is exactly what real science looks like. The current suite of missions, Curiosity, Perseverance, the Ingenuity helicopter, which demonstrated powered flight on another planet for the first time, China's Zhurong rover, and a fleet of orbiters from NASA, ESA, the UAE, and others, represents an unprecedented level of study of any planet other than our own. And the Mars Sample Return mission, when it eventually flies, will bring back the first physical material from Mars ever examined in Earth laboratories. That is a significant scientific moment whenever it arrives. Mars is a planet that had its chance. A thicker sky, running water, geological heat, the right chemistry, everything that life as we know it requires. Whether anything took advantage of that window, and what became of it, is perhaps the most compelling open question in planetary science today. It's also not purely academic. Understanding how Mars lost its habitability tells us something about how rare, or how fragile, the conditions for life might be, even in a solar system like ours. The answers are coming, slowly, carefully, in rock cores and radar returns, and spectral analyses. But they're coming. If you've been following this series, the full Mars playlist covers everything from the planet's formation through to today. Worth watching in order if you haven't already. Next time, we leave the surface entirely and look at Phobos and Deimos, the two small moons of Mars, and why they're stranger than they first appear. If this is the kind of science you want more of, subscribing is the straightforward way to make sure you don't miss the next one. That is part 5 of Mars. In part 6, we explore the next key question. Subscribe so you do not miss it.